Thank you. I always do forget that. Okay.
I think our record is like 80%. It's really good.
All right.
Yay,
Friday. Last Friday in September. You can see I filled in next week with lots of good problems to work on. Also Monday we've got a couple of star problems due, and today we're going to finish up. We're going to do section 4, which is the chain rule, which is not the sexiest of all mathematical topics, but it's certainly necessary, and so we're going to work our way through that. Before I do that, what I'd like to do is answer any questions that you might have on the current homework and the current web work.
We go over on the web work. You had sent an email about the second derivatives or something, I think.
Oh yeah.
Like 6, 7, and 8, somewhere in there.
Yeah, I threw those in there really just to kind of foreshadow, what was coming up. So you figured out that f sub x means to take the partial of f with respect to x. F sub y means to take the partial of f with respect to y. I just threw this in there. What I was kind of hoping that you might figure out is that f sub xy is you take the partial of y with you take the partial of f sub x with respect to y. Take the partial of f sub y with respect to x. In other words, find the partial of f with respect to x. Whatever that is, take the derivative of that with respect to y. Okay, same thing over here. Take the partial of this with respect to y, and then take that and take the derivative of that with respect to x. And those of you that did this one, what did you notice about those? They were equal, and that was not an accident. There's a theorem that we're going to learn, gosh, maybe Monday, but maybe later. Yeah, Monday. There's a theorem we're going to learn called Clairaut's theorem that actually proves that mixed partials are equal. F sub x, y. In other words, the order in which you take these derivatives doesn't matter. And that's, I think, a somewhat surprising result. That if you take the derivative with respect to x and then y, you get the same thing as taking the derivative with respect to y and then x. I don't know. It's just kind of interesting. It actually plays an important role in Calc 3 as well. The fact that mixed partials are equal can simplify expressions. It's really useful in certain theoretical derivations. Other questions on web work? Okay, if you guys don't have questions. Yes. Okay. Okay. You know what? I'm going to talk about, I'll come back to this one. I want to talk about, I think 10 and 11 first. And then I'll come back to 9 because they're all related. So even if you don't have questions about these guys, I want to talk about it. So I like this problem because it's a qualitative exploration of these highly quantitative objects. it develops your intuition for what these quantities mean. So let's look at this problem here. If you look at this thing, you see there are little words, low, medium, and high. And the suggestion is that the darker the color, the lower the value. The brighter the color, the higher the value. So if you were to imagine the surface that's described here, it would be a kind of rising up like that. So it's low down here and it rises up. And you're asked to figure out the sign, SIGN, of various partial derivatives. Let's talk a little bit about that. So we've got this point P, and we're asking, well, what is the sign of the partial of f with respect to x? What's the sign of the partial of f with respect to y? If you don't know the geometry of these quantities, then you're going to have a hard time answering this question. And so let's talk about the partial of f with respect to x. That is essentially telling you the slope of the surface in the direction parallel to x. All right? So if I look at a little area around P and I imagine this parallel direction to x, what happens as I go from left to right? Am I climbing up or am I falling down? I'm rising because I'm going from what appear to be dark areas to light areas. Dark areas are low, light areas are high. So it appears that I'm going up. And you have to imagine or kind of extrapolate or interpolate P as a point, right? And you have to try to figure out, like, at that point, how is the surface slanted? And here we see that it's going up. That suggests that the surface is increasing in that direction, which suggests that the partial of f with respect to x is positive. So it's one of those two guys, right? Okay, and then let's look in the other direction. Parallel to y, going from bottom to top, that's the positive y direction. I'm going from a darker area to a lighter area, so it's increasing. And so again, the partial of f with respect to y is positive, and so this guy corresponds to number 4. Okay, good. Let's look at the next one, and then I'll go back and look at Tabo's question. So the next one is quite similar. You're asked to determine whether a particular partial derivative is positive or negative at a particular location on this graph. Again, the low spots are dark, the high spots are light. If you were to visualize the surface, what would the surface look like? It's a bowl, definitely. It's lowest in the middle, and then it goes up around the edges. One example of such a surface might be the paraboloid, z equals x squared plus y squared, and in fact, this probably came from a paraboloid, the person that generated this problem. Okay, so let's look at f sub x at the point Q. So here's Q. F sub x is, how is the surface changing right here at Q? Well, we can see that in a broader stretch, it appears to be going from light region to a dark region, which suggests decreasing. The idea is to take that and kind of use it to extrapolate what's going on right at the point Q. And so if, just for the sake of this exercise, if it's decreasing from here to here, then it's safe to assume that it's decreasing right there, right at that point. So that means f sub x is negative. And you can go all the way around the circle and visit all these different points, and in fact it looks like that's what they did. There are 8 questions here, there are 4 points and 2 partial derivatives at each point. Any questions about that one, Lila?
I got this one, but in what instance would it be 0 at the center?
Yeah, I mean, you don't really have enough information from this fairly coarse diagram to say precisely. So there's a lot of inference going on here. The inference is that this is smoothly sloping down to a minimum at the origin. And so I agree with your intuition there that there's probably a minimum in here at the center. But you know, even out here, right? Who's to say that right, that maybe this is some peculiar step surface, right, where it's level and then level and then level and then level, right? In which case, all these partial derivatives are 0. All right. So yeah, I agree with your intuition there, that there's a minimum at the origin, and at that point in the origin, both fx and fy would be 0. Okay. Other questions about this problem? All right, so now that we've looked at this, let's go look at a problem that's similar to this, except rather than looking at level curves and what I call contour plots, we're actually going to look at the surfaces. So this is a really similar exercise, except we're actually looking at the surface now instead of some contour plot or some gradient plot. So let's try to answer some of these questions. F sub y at the point A. So here we are at A, and F sub y is the slope in the direction parallel to the y-axis. So it's really important that you figure out which axis is which, right? And so we see here by this label y and x that this is the y-axis, this is the x-axis. So our partial derivative here at A is going along parallel to this thing. Okay. Well, what do you think? Oh, and it's also important that you figure out which direction is increasing y. Okay, so here I am, increasing y is this direction. Here's a slope. What do you think, f sub y, positive or negative? It's negative because the surface is going down in the y direction as y increases. Okay, let's keep going around the circle here. B, f sub x. So that's parallel to the x-axis. This is increasing x. F sub x, negative. Let's keep going. F sub x at A is here. Increasing x parallel to x, positive, good. And f sub y at B, increasing y, negative. Okay, what's your question, Tavo?
Oh, those ones I got.
Good.
So I guess I rotated the picture so way that I can.
Oh, okay, so maybe, yeah, it's
And also,
really...
it says does the sign change from A to...
That's an excellent question. So the sign changes, one of the partial derivatives changes sign as you go from A to B, and one doesn't. Which one changes sign as you go from A to B? F sub x. It goes from increasing to decreasing. So it goes from positive to negative. And the other one actually doesn't change sign. It might change, but it's not going to change sign. F sub y is negative the whole time. Okay. Any other questions on this web work? Now, one thing that I didn't ask in web work because I couldn't find any particular problems, but that you are responsible for is, let's go here and here. I didn't talk to you about, or I didn't give you any web work on finding the equation for the plane tangent to a surface at a point. And on Wednesday, I showed you my approach to doing this. What I want to very quickly review today is the book's approach, which is different and perhaps somewhat easier to understand at this stage of the game. So if you flip back a few pages in the book, remember what you need to find a tangent plane. You need a point and you need a normal vector. Okay, I think I've gone too far. You need a point and a normal vector. And my normal vector, what I was doing was finding the tangent vector in this direction, finding the tangent vector in this direction, taking the cross product, and getting the normal vector. Well, what Gashart did in his book is he generalized that, and it's probably worth pointing out to you, although you should be reading and pointing this stuff out to yourself, it's probably worth pointing out to you that you can very quickly generate the normal vector at a point on the surface using this formula. Partial of f with respect to x, comma, partial of f with respect to y, comma, -1. And so what I thought I would do is use this formula on the example that I'd done last time, which was, oh boy, which was this. So let's find
The regular one needs to work too. Does it have to be -1?
it has to be -1. Yes. Either that or minus f sub x minus f sub y 1. So the sign does matter. So if you use f sub x, f sub y, it has to be -1. If you use minus f sub x minus f sub y, it has to be 1. Okay. We'll talk about why that's the case a little bit later. So find the equation of the tangent plane to the surface. Z equals, and this is the same one that I did last time, y cosine x minus y at the point 2, 2, 2. Okay, and from the book, we have that the normal vector in general can be written as the partial of f with respect to x, partial of f with respect to y, and -1. So if I'd like to find the normal vector at this particular location, it'll suffice to compute f sub x, which is I think that's f sub x. Yep. F sub y, which involves a product rule, sadly. First times the derivative of the second plus the second times the derivative of the first. Okay, there were a lot of minus signs flying around in this thing, and I didn't point them out to you. I'll point them out to you now. When I want to take the partial derivative of this thing with respect to y, first of all, because there's a y here and a y here, I have to use the product rule, right? First times the derivative of the second. The derivative of the second is, first of all, minus sine x minus y. But there's another minus sign that comes out of the chain rule, right? And so the minus sign turns into a plus sign because of that. So that's why the first term here looks like y sine x minus y. The second term is much easier. First times the derivative of the second is this guy. Second times the derivative of the first. Derivative of the first is just 1, right? And so we get cosine x minus y. So we have f sub x and f sub y in general. We're, of course, not interested in these guys all over the surface. We're only interested in them when what? When x is 2 and y is 2, right? Okay, so at x equals y equals 2, we get n is, well, what is n when x equals y equals 2? Well, you plug that into f sub x, and what do you get? 0, good. And in y, f sub y, you actually get 1. And then, of course, the last coordinate, as Ethan was struggling with, is -1, period. It is what it is. Read the derivation in the book. Okay? It has to be -1. If you compare that to what I did on Wednesday, I think the normal vector that I got on Wednesday was 0, -1, 1. How do I explain the difference, the discrepancy? Yeah, so for lack of a more detailed picture, one of these vectors is pointing normal this direction, and the one is pointing normal in this direction. Are either one of these okay for doing a plane? Yeah. So I'm fine. Okay, so now build the plane. The plane is then just 1 times y minus 2 minus 1 times z minus 2 equals 0. That'll do with a bit of simplification. Y minus 2 minus z plus 2 equals 0. The 2's cancel, and I get z equals y, which I think agrees with what I did before. So that's the tangent plane. Just to show you that I'm not making this stuff up, what I wanted to do now was I want to plot both the surface and the plane on the same axes and show you that in fact that this plane is tangent to the surface. So let me flip over to Maple. Looks like my network is going to give me trouble again. Well, we'll just hope for the best. Maple actually needs the network to get its license. And I'm not optimistic given that little exclamation point down there. But sometimes, you know, the exclamation point's there and everything's working fine. Yay, computers. Okay. Oh, so far so good. See if I can plot something. Okay, whatever. Let's switch over to this. See if that one works. Yes, sure, I'll exit Maple. Ooh, another exclamation point. No, it's just because it's dumb. One of these days I got to get myself an Ethernet cable in here. Ethernet never does this. I could use the porch, which is probably across the street or something. Or the circus. Good Lord. There we go. Okay. Let's hit it while it's still working. Because once I get the license, then it'll work. And I don't care if the network goes down. Yeah, exactly. Right. Well, yeah, but you know.
Rip the DRM out of it.
I don't want to get sued by Maple. It's true. Let's just not go there. Okay, so I'm going to plot the surface, which was I have written in my notes because I don't remember it right now. And let's see, a good range over which to observe this surface would be something like, say, x equals 0 to 4 and y equals 0 to 4. Why do you think I chose those ranges?
Just over pi.
Meh. Better reason.
Oh, because 2, 2, 2 is in the middle.
Right, 2, 2 is right smack in the middle of both of those, right? X equals 2, y equals 2. So if I'm gonna see what's going on at this point 2, 2, might as well just stick it right in the middle. All right, so that's why I did that. Let's get the plane. That's also another 3D plot, and it's a simple one. It's just z equals y, and we'll go over the same range. Okay, and I'll just display both of these guys on the same axes. So that's surface and plane, and see what happens. Okay, and let me turn on the axes here. All right. So yeah, we definitely see something that looks like it might be tangent to the surface here. It's a little bit difficult to see where the point is. Let me drop a little marker in there to show where the point is. Okay, the point was 222, I think. And let's make it big. And make it red. And add it to the list. Okay. Well, it's not quite big, but at least we can see it. Okay, so there's the point of tangency that we actually developed. It turns out that this point of tangency is not alone, right? This plane appears to be tangent all along this ridge on the surface, which is mildly interesting. You can see that that point lies right in the middle. If I sort of come up, look down from above, right? That is right at the point x equals 2, y equals 2. Yeah. And this is a reliable way of generating a tangent plane, right? You find the normal vector, f sub x, f sub y, -1, and a point, and there you get the tangent plane. So it's pretty straightforward. All right, questions about that? All right, let me go on then and talk about the topic of the day, which is the chain rule. So the chain rule, I'm not gonna prove it. The book proves it. I'm gonna just motivate it with an example, and I'm gonna start by reminding you what the chain rule is in Calc 1, and then through an example, I'll motivate its generalization, and then we'll just apply it to a few examples, and then we should be moving on to our weekends. Okay, so the chain rule. This is section 14.4. Okay, so for the chain rule, maybe you remember maybe you remember from Calc 1. Say if let's say you have a function, let's see, g of x and h of t. Oops. And you form the composite function. Then f is really a function of t, and the function of t is obtained by taking h and substituting in it for x. Right. So I can build a function of t that is this function of x composed with this function of t. And the chain rule gives us a really convenient way of finding the derivative. It says the derivative of f with respect to t is the derivative of g with respect to x times the derivative, and that's evaluated at h of t, times the derivative of h with respect to t. Okay, that's something that you know and love. That's something that you do all the time. In fact, we did it in just the previous example when we were differentiating y cosine x minus y. There was a chain rule in there where minus 1 popped out, right? Okay, so that's something that even if you're not like totally up on the notation, it's something that you use all the time. All right, let me, by way of example, let's try to generalize this notion to functions of several variables. And we'll start with a function of two variables. Let's consider f x y equals x squared y plus x y squared. Okay, and let's pretend x and y depend on t. So there's no t in the picture at all. Let's just pretend that they depend on t. So we've got this function f of x and y, x squared y plus xy squared, and secretly x depends on t and y depends on t. So the Wizard of Oz here is t. Behind the curtain is t. T controls x and y control f. Right? And so what you might want to ask as a mathematician or an engineer or a physicist is not how does f change with x and y, but how does f change with respect to t, the true master. Does everybody see what I'm talking about? So we're pretending that x and y depend on t. And so when I change t, I change x. When I change t, I change y. And so through t and through x, I'm actually changing f. So a natural question to ask is, what's df dt? Well, you have to go back and remember your implicit differentiation skills, again from Calc 1. And so let's do a bit of an aside here. Okay, implicit differentiation in 2 minutes or less. X squared plus y squared equals, say, r squared. That's the equation of a circle, right? Now, if I set a value of x, say I set x equal to r, what's y? 0. So y is determined by the value of x. Yeah? So a mathematician would say that y is actually a function of x. Whatever I set x to, that's going to determine y up to a plus or minus. Okay? And so the mathematician naturally wants to ask, well, how does y depend on x? What's the derivative of y with respect to x? And that's what implicit differentiation was. Right? Instead of explicitly having y equals some function of x, we have x and y all tangled up with each other in some expression, and yet we still want to know how y changes with respect to x. So we pretend that y is actually a function of x. And we take the derivative of the whole expression with respect to x. Oops, plus. And the regular old chain rule demands that we put a dy dx there. And what's the derivative of the right-hand side with respect to x? 0. Okay? R does not depend on either x or y. Let's just leave it at that. Okay. And where did you go from here? Do you remember in implicit differentiation? Exactly. We solve for dy dx. So if we solve for dy dx, what we get, let's see, common factor of 2 minus x over y. We get minus x over y. Now, one of the oddball things about implicit differentiation is you get the dependent variable showing up in your derivative. And that's something that doesn't happen in regular differentiation, right? You don't get the y showing up in there. But, in fact, this derivative still carries geometric meaning. For example, if I'm up here, what are the x and y coordinates of that point up there on a circle of radius r? X is 0, y is r. So if you come over here and you plug in x equals 0 and y equals r, what do you get? 0. And that tells me that the slope of the curve at this point is 0. Do you buy that? Yeah. Okay. Let's go around here and see, do the same thing over here. What are the x and y coordinates there? Negative r and 0. And what does that give you when you plug it in? Infinity or undefined, right? And in this context, undefined means what kind of tangent line? Vertical. So yeah, this still works as the slope of the curve, even though it has both x and y in there. Okay, so that's the aside. That's kind of what I want to do up here. So now, in fact, before I go here, let me go up here and let me rewrite this as x of t squared y of t plus x of t y of t squared. Right, so now I'm showing you, I'm sort of through my notation, I'm showing you that x depends on t and y depends on t. And I want to take the derivative of this thing with respect to t. Okay, if I'm going to take the derivative of this thing with respect to t, here's two functions of t. What do I have to do? Before I do chain rule? Product rule. So it's first times the derivative of the second plus the second times the derivative of the first. Second times the derivative of the first is 2x y dx dt. Yeah, let me switch those around just so that you it makes more sense when you read it later. Okay, that's just the first term here. So the first times the derivative of the second, x squared times dy dt, plus the second times the derivative of the first. Derivative of the first is 2x to the first power times the derivative of x with respect to t. That's where all that came from. Everybody still with me? All right. Let's do the same thing to the second term. First times the derivative of the second. Oops. Plus the second times the derivative of the first. That's a pretty messy expression. What I want to do is I want to collect terms. I want to collect on dx dt and dy dt. So let's do that. And I want to collect on dy dt. Does everybody see what I did there? I just collected all the terms with dx dt, grouped them together, all the terms with dy dt, grouped them together, and factored out the dx dt and the dy dt. Now here's where I motivate the chain rule for functions of several variables. Does anybody see how this expression is related to this expression? Be more specific. That's the partial derivative of f with respect to x, isn't it? And what about the thing in the second parentheses? Yep. And it turns out that's not peculiar to this example. It happens all the time. So the chain rule the chain rule for two independent variables that depend on some other variable is exactly that, and it's always just this formula. So if you want to compute, so remember the original scenario. F depends on x and y depend on t. And the mathematician wants to know, how does f vary with t? Cut out the middlemen, right? Get rid of x and y. How does f depend on t, which is really running the show? The way to figure that out is to find the partial of f with respect to x, partial of f with respect to y, partial of x with respect to t, partial of y with respect to t, and form this expression. Okay? This mostly has theoretical applications, although you do have a few exercises where you have to compute it, because in fact you could, if you wanted to, just take this expression right here and differentiate it with respect to t, right, and get the same answer. All right, so let me do let me do an example. Oh, before I do that, let me do an example. Okay. Oh, come on. Okay, so here's what we're really talking about. Problem 1, for example. So we have z is a function of x and y, and both x and y are functions of t. So what we really want to know is, how does z depend on t? All right, so let's go do that. I forgot already. T squared plus 3 and t cubed. Okay. So there's the setup for the problem. And the question is, what's dz dt, right? Z depends on x and y depend on t. How does z depend on t? How does z change with t? That's dz dt. Well, to compute that guy, we know that we have to find f sub x times dx dt plus f sub y times dy dt. And so we're going to have to build all these pieces. So we're going to get f sub x by taking the derivative of this thing with respect to x. That's going to be 2x cosine x squared plus y squared. F sub y, 2y cosine x squared plus y squared. We also need dx dt. That's 2t, and we need dy dt, and that's 3t squared. Is everybody still with me? And I take all of these guys and I plug them in, and it's pretty messy. It's going to be 2 times the quantity, t squared plus 3 times the cosine of t squared plus 3 all squared plus t to the 6th times dx dt, which is 2t, plus 2 times t cubed cosine quantity t squared plus 3 all squared plus t to the 6th times dy dt, 3t squared. Probably you could do some simplification here, but let's just stare at it in all of its algebraic glory and figure out what I just did. Where did this come from? It's the partial of f with respect to x, plugging in what x and y actually are in terms of t. So for example, this guy, f sub x is sitting here. 2, x is t squared plus 3, And then x squared is t squared plus 3 all squared, and y squared is t to the 6th. And then there's this dx dt right here, 2t. And I did the same thing for the second term. Okay? You could just as easily, I think in this case, you could just as easily form the following. Try to get both of them on the screen at the same time. Instead of leaving z as a function of x and y, I could just stick x and y in at the beginning, like that. You see what I did? And then I could just take the derivative there. And you can do that, and you can confirm, I'm not going to do it, but you can confirm that z prime of t gives the same result. All right. So I would wager that neither is particularly easier than the other, and that's why I said you're doing a few calculations here to understand this, but this multivariate chain rule really is more for theoretical stuff that we're going to do later, because to be honest, it's probably just as easy in most cases to substitute in and take the derivative. Okay, but when you're doing these exercises at the end of this section, promise me that you're going to do it using the chain rule formula. Okay, I want you to understand it, know how it works, see some of the patterns. All right, let's keep going then. So you're going to run into some exercises like this. What if okay, so I'm upping the ante here a little bit. What if instead of x and y depending on one variable, t, x and y depend on two variables, s and t? Okay, so now we have z depends on x and y depend on s and t. When I wiggle around s and t, I move around x and y, which moves around z. And what I want to know is, how does z depend on s? How does z depend on t? Once I have the situation worked out up here for this previous example, it turns out that this is not going to be nearly as miserable. So this follows. And I guess what follows? What if that, or what is? So what is partial of z with respect to s, or partial of z with respect to t? Well, you remember how to take partial derivatives, right? You take the derivative with respect to s, you just treat all the t's as constants. Right? You take the derivative with respect to t, you treat all the s's as constants. And so the only thing that changes in the chain rule above is, instead of having Roman d's everywhere, I have script d's everywhere when I take my derivatives. Let me show you what I mean. So for example, the partial of z with respect to s is going to be the partial of z with respect to x times the partial of x with respect to s, plus the partial of z with respect to y times the partial of y with respect to s. And again, really the only difference between this expression and the expression upstairs is I had Roman D's here instead of script D's. The script D's are a signal to the reader that, hey, X depends on more than one variable. Okay, a lot of this stuff is implicit. So I'll write the partial of z with respect to t, but stare at it for a minute, see if you can guess what it's going to be. So that tells me how z changes with respect to t, tells me how z changes with respect to s. And one last escalation. Suppose w is equal to f of x, y, and z. So now instead of having a function of 2 variables, we have a function of 3 variables. And let's pretend that, just for the heck of it, that x, y, and z depend on s and t. I've done that. You don't really want to. It's just sort of part of some larger problem that you're dealing with. Okay. There's not really any reason that you should be able to figure this out, so I'm just going to point it out to you. Partial f with respect to x times partial x with respect to s plus partial f with respect to y times partial y with respect to s plus partial f with respect to z times partial z with respect to s. How does this compare to the chain rule with x and y? How does this compare to this? What do you notice? There's just one more term for that one more variable. And this goes on ad infinitum. You can have a function of 4 variables, you have 4 terms. 5 variables, you have 5 terms. Just a bit of foreshadowing here. It's not an accident that this is actually the dot product of these two quantities. And we'll talk about that some next week. Does everybody see how that's the dot product? Okay. And that thing in the front there is called the gradient. Of f. And that's what we're going to talk about next week. Okay. Let's look at a couple more examples, then I'll review the web work, and then I will set you free. So 1 and 2 are just the straight up x and y depend on a single variable t. 3 and 4, x and y depend on 2 variables, s and t. So we want the partial of z with respect to s, partial of z with respect to t. What about something like 5 or 6? Use the chain rule to compute partial z with respect to x, partial z with respect to y. Okay, this is one more kind of way of doing this problem, and it's sort of the Calc 3 version of implicit differentiation. So let's do number 6. Number 6. So 2x squared plus y squared plus z squared equals 9. And then let me remind myself what we were actually going to do with that. We want the partial of z with respect to x and the partial of z with respect to y. Okay. This is weird because z isn't isolated on the left-hand side. Z is all tangled up with the x's and the y's. So this is like partial differentiation. Implicit differentiation. Okay, let's work our way through this. So what we're going to do is we're going to pretend that z is a function of x and y. X is a function of x, y is a function of y. Okay, and we're going to differentiate both sides with respect to, say, x. So for this guy, let's differentiate the equation with respect to x. Okay, so what's the derivative of 2x squared with respect to x? Four x. And the derivative of y squared with respect to x? 0. And the derivative of z squared with respect to x? Nope. Remember, we're pretending that z is a function of x and y. It's the partial of z with respect to x. Right? It's all about what we're pretending. And what we're pretending is z is a function of x and y. So, where do we go from here? We were trying to find this guy. Solve for it. So what we get is the partial of z with respect to x is what? Negative 4x over 2z. And that's negative x over z. Okay? So implicit differentiation works the same way. Did I screw something up? Yes, thank you. Okay, so the point of this exercise is that implicit differentiation works with partial differentiation. So it's just a matter of how many variables you're assuming are in play. I'll let you figure out dz dy. Let's go back to the text here. Double check here. So the answer is up there in the upper right corner, negative 2x over z. Okay. So this kind of problem is really just reaffirming the fact that partial derivatives, you can do partial implicit differentiation as well as straight up implicit differentiation. All right, let's go back and look at one last problem in the book. So chemistry people in the room will know and love problem 7, maybe not love. PV equals nRT. It's been a long time for me since I've actually had to deal with this equation. PV equals nRT. And P is pressure, V is volume, T is temperature, N is like the number of moles, I think, and R is some constant that I don't know. Oh, the ideal gas constant, yes. Oh yeah, it's all written up there. Yes, I should just read. All right. Now, what's interesting about this is very similar to what I just did in problem 6. Right? We've got P, V, and T are all tangled up with each other in this relationship. And it's just like X, Y, and Z are all tangled up with each other in this relationship. Okay? And what we want to do is try to answer some of these questions. based on that relationship. So let's look at part A. If the pressure of a gas is increasing at this rate and the temperature is increasing at this other rate, how fast is the volume changing? So here we're assuming that all of these quantities, P, V, and T, are dependent on some other variable, right? What variable is that? Time. And what we want to do is, let's see, how fast is the volume changing? So what do I want to find? I want to get my hands on dV dt, right? Yeah? Okay. So let's try to do that. So we want dV dt, and we know that PV equals nRT. And so what we're going to do is we're going to pretend that all these guys depend on T. P, V, and T all depend on little t. And let's take the derivative with respect to time. Okay, so that's my mathematical way of saying assume that P is a function of T, V is a function of T, and T is a function of little t. And that they're all tangled up in this relationship. All right, so if I want to get my hands on dV dt, I have to differentiate this with respect to t, right? That's clear? But what may not be clear is now, for example, when I differentiate this with respect to t, what am I going to have to do? If both p and v are functions of t and I differentiate them with respect to t, I need a product rule.
Would it be easier to just move the t to the other side?
Yeah, I mean, you could do that too. I'm going to keep it on this side just to sort of make the point that I don't have to do that in a more complicated expression, right? So PV equals nRT is a fairly straightforward expression, but other physical expressions can be really complicated, and then isolating a particular variable might be impossible. So, but what Andy said is absolutely correct, and in this case, it's probably easier. Maybe not, though. Anyway. So we get P prime V plus PV prime. That's the product rule on the left-hand side. What's the right-hand side with respect to time? How do you take the derivative of that? What's that going to be? It's not as hard because N and R are constants. N R T prime, big T prime. So it gets weird on the left-hand side because of the product rule, but the right-hand side is pretty straightforward. Okay. Now, what of these quantities do we seek? We seek this guy. And which of these quantities do we actually have? We actually don't have all of them. We know N and R. Let's go see what we do have. We have the pressure, which is increasing at a rate of 0.2, which tells us that P prime is what? 0.2. And we have the temperature increasing at a rate of 1 Kelvin per minute, which means that T prime is 1. Okay, so P prime is 0.2. And T prime is 1. And we seek V prime, so we solve for V prime. And then isolate V prime. And that's, sorry, that's a P. Yes, you're right. And that's, even that sometimes, and that's not a V double prime, even that isolation step might be difficult or impossible, depending on the expression that you're dealing with. So sometimes you might do all this, and you're still stuck with having a tough time at getting at the quantity that you want. But in this case, it wasn't so bad. Let's see if we're actually close. So this is 14.47a, 14.4.7a. Yeah, that looks right. Okay, and then I'll let you play around with the others. Okay, let me really quickly talk about web work. Oh, and the network is dead. Yeah. Which one am I on? I'm on that one. Let's try the other one. I'll just keep switching back and forth. Okay. So there's only 6 problems here, but don't let that lull you into a sense of complacency. So this is an exercise in following the chain rule where z is a function of 2 variables and each of those variables is a function of 2 variables. And this lets you compute all of the pieces of the chain rule. You don't actually have to finish it off, but you get all the pieces. Let's keep going. Here, similarly, z is a function of 2 variables. Each of those variables is a function of 2 variables. You have to compute all the pieces, and you have to put it all together. I just put this in here because I like this comment. But it's the same thing. This is the one I want to briefly discuss because I think it's a little opaque to the beginning reader. Okay, so f of u and v is a function of 2 variables. And we are going to let the partial of f with respect to u be called g, and the partial of f with respect to v be called h. And they're asking you to find f prime of x for these various cases. So f of x is what you get by taking x and 5 and plugging it in here. So does everybody see that even though f starts out as a function of 2 variables, if we plug in x and 5, then the result is going to be a function of 1 variable, right? Because all the v's are going to be 5s and all the u's are going to be x's. And so there's only going to be 1 independent variable when you're done with that. And what we want to know is how do we take the derivative of that thing given the information available to us. So to take the derivative of this thing, it's f sub u times the derivative of this guy with respect to x plus f sub v times the derivative of this guy with respect to x. Okay? What's the derivative of this guy with respect to x? It's 1. What's the derivative of this guy with respect to x? 0. And so the net result is going to be the partial of f with respect to u evaluated at x and 5. That's going to be g of x and 5, right? Okay, let's keep going. Now I've switched the roles, but when I plug in 5 and x, I still just get a function of x. The partial of f with respect to with respect to u times the derivative of 5 with respect to x is 0. Plus the partial of f with respect to v times the derivative of x with respect to x, which is 1. So this is the partial of f with respect to v evaluated at 5 and x, which is secretly just h of 5 and x. Let's keep going. Exactly. Partial of f with respect to u times the partial of x with respect to x. So that's just the partial of f with respect to u. And then the partial of f with respect to v times the partial of x with respect to x, another 1. And so what this is going to be is g of xx plus h of xx. All right, finally, this is where it gets interesting. F sub u times the derivative of this with respect to x, 5, plus f sub v times the derivative of this with respect to x, 2x. So that's going to be g of 5x x squared times 5 plus h of 5x x squared times 2x. So I've just done it for you once. You need to go home and do it again and make sure you understand it. I don't know if there's anything else worth yapping about. I don't think there is. Have a nice weekend.